All right, in this lesson, we're going to be exploring how we can build a polynomial regression equation for a set of data. So as we learned in grade 11 applied, a regression equation is an equation that we build through Desmos that approximates the curve of best fit based on the data points that are provided in the data table. Now, there's many different ways that we can do regression analysis. In Applied 4DS, we will continue to use Desmos. So you will need to refer to the very important document that was provided on my website, the function regression models. So these are the models that we'll actually be using. I did include linear for the sake of remote learning and the time frame. We're not going to be doing any linear examples. However, we'll be doing the rest of them. So for polynomials, we'll be referring to the quadratic and the cubic. So note that in a regression model, there is no equal sign, okay? There is the tilde, okay, the tilde symbol. Notice as well that there is a number 1 underneath the y and the x, and that refers to the data table that we are going to insert into Desmos. Okay, so this is not actually an equation yet, because remember that an equation needs an equal sign. So this is the model that we are going to be typing into Desmos, and it's going to basically be asking Desmos to find the quadratic model or the cubic model or whatnot that will match the data that we plot in. The letters A, B, C, and D are the constraints, so they would be the different coefficients. A and B and C would be coefficients in the cubic example. The final one, whether it's a B, a C, or a D, the final value is a constant term, remember, and that constant term represents the y-intercept of the graph as well. It also represents the initial value. So that's going to be very important. So again, in Desmos, we'll be getting the values for A and B and C, or A, B, C, and D, and then we'll be just substituting them in place of the A, B, and C, and D. And so I'll show you some examples as we go through the notes. Okay, so when we're doing our scatter plot in Desmos, we'll be looking to do a curve of best fit, and that's what Desmos is going to do when we actually type in the regression equation. So a curve of best fit is a curve that approximates the trend that is displayed on a scatter plot. Remember that a scatter plot is a graph that just has points that are plotted on it. For polynomials, we're either going to be doing a quadratic regression or a cubic regression in this unit. And again, refer to the regression models for Desmos handout that was provided. So we're going to go through 4 examples today. We're going to do 2 quadratics and 2 cubics. The first examples, the first example for each will be just a basic level 1 where we have some data without context. Then we'll be going through an example with context. Then a cubic regression without context, and then a cubic regression with context. Okay, so whenever we want to determine quadratic regression model, or any regression model for that matter, we have to open up Desmos. And so what we're going to do, so I'll just close this off. So what we will do then is plot the X, Y data points in our table. So we go to Desmos, we click the plus, insert table, and you'll notice it says X1 and Y1, and that's why those numbers are there in the regression models. So we'll just type in the X data. It goes 0, 4, 10, 13, 0, 4, 10, 13, and we'll type in the Y values, 15.6, 18, and then 10 and 13, nope, and then 12.6 and 5.85. 12.6 and 5.85. Okay. So right now we see nothing. So we're going to scale our X and Y axis. So we'll say our X axis minimum of -1, and we'll make it go to 15. And then our Y will start from -1, and we'll set it, goes We'll set it to 20, maybe 25. Okay. Okay, so clearly here now we see some data points that are plotted, and this would be considered a scatter plot. So when we get a scatter plot, that's what the scatter plot looks like. It's just points. So to get the regression equation, okay, for quadratic, we will type in the regression equation model, which again, I shouldn't have closed it. Okay. So we're going to type that in directly. Okay, y1 tilde ax1 squared plus bx1 plus c. So y1 tilde ax1 squared plus bx1 plus c. And as soon as we do that, you'll notice that we have a quadratic regression and we have a curve of best fit. Okay, so we now have our curve, we're good to go. So a few things. We're not going to talk too much about r squared, but r squared is a measure of how accurate the regression model fits, or how close it fits to the data. And so it ranges from either a 0 to a 1. So that would be 0 to 100%. So 1 would represent 100% match. So this perfectly fits the data point. For example, if I say I changed this 18 to a 28, then you would notice that it still makes it a quadratic, but it doesn't fit as well. It's only 87% accurate. So the r squared in this course, we're just going to refer to how accurate the regression equation is as it relates to the data. And that's about as far as we would take it. What we are going to concern ourselves with are the values for A, B, and C. So when we're doing our work and we want to get this, like we want to get our work to show how we got the data or how we get the regression model, we are going to want to snip this graph. So I would expect that we would snip everything. We want to see the data points, we want to see the graph, and we want to see the actual regression work. So we'll open up the snipping tool. And we will snip the graph. Copy it. And we will paste it in. And we can make it a bit smaller. And there we go. Good. Okay. So what we're going to want to do now is type in the values for A, B, and C. And again, we're just going to pull it off from Desmos. So A equals negative 0.15, B equals 1.2, and C equals 15.6. Okay, so our regression model was y1 tilde ax1 squared plus bx1 plus c. So that is what the model is, but we want to have the equation. So to do that, I'm going to turn y1 into y equals, now instead of a, we're going to put the coefficient. So negative 0.15 x squared plus, instead of b, 1.2, so 1.2x plus 15.6. So this would represent the regression equation model that approximates the data. A very common mistake is that students will leave the Desmos model in place, but again, we want an equation, so we have to have that y equals. And notice that we do no longer have x1 and y1. Okay, when we have an equation, we just have x and y. Also note, if there's context, then we have to make sure that we use the proper independent and dependent variables. But in this case, there is no context, so this would be our equation. Rounding, we should always take it to 2 decimal places, but again, the B value and the C value terminated at the 10th, so we don't need to add the zeros. We can leave it as a 10th, but if it goes further, we typically round at 2 decimal places, so just be aware of the rounding. So that is sort of how we go through a quadratic regression model. So we'll now look at an example in context and use it to solve a real-life problem. Okay, so there's some data collected that we have in this table. It says the following data shows the relationship between the speed of a car and the stopping distance of the car. So how long it takes the car to stop based on its speed. The speed S, so now we have a contextual variable. Okay, so the speed S is the independent variable. It's in kilometers per hour, and the stopping distance D is in meters. It's the dependent variable. So the X is essentially the speed, which we use S, and the stopping distance is the Y, which we are referring to as D. So we have to make sure that we refer to S and D instead of X and Y. Okay, so the first thing we're going to do with this to solve this problem is that we are going to go back into Desmos and get a scatter plot, and then we're going to see what type of polynomial function we might recognize. So we can go up here and we can just reset Desmos and then insert the table and go from there and build the data table just like we did in example 1. So we insert table. So we have x1 and y1. So again, the speed is like our x and the stopping distance is like our y. So I'll just put that in red. That's like our x and stopping distance. Okay, that's interesting. Well, speed is x, stopping distance is y. So we'll add in our x's first, 90, 36, 63, 24. So 90, 36, 63, 24. And the stopping distance y, 94.4, 17, 43.1, and 10.9. Okay. So now we can't see anything, so we can zoom out a bit more, and there we go. So what we need to do next is put in our labels. So our x-axis, remember, is the independent variable, which in this case is the speed in kilometers per hour. So we'll type speed in kilometers per hour. And our y-axis is stopping distance, and that was in meters. So we have our axes labeled, and we have our scatter plot. So if we look at the curve, or sorry, when we look at these points, we want to recognize the polynomial function. So it kind of is going down, and it might come back up. So this might look like a portion of a quadratic. So the scatter plot approximates a quadratic relationship. Okay, so it kind of looks like a quadratic relationship. We'll put that in red. All right, so now we want to determine their quadratic regression. And just for fun, it's asking for 3 decimal places. So again, always go based on the problem. If the problem tells you to round to a certain number of decimal places, then make sure you follow that. If not, then you can always just sort of use the basic 2 decimal places. But in this case, it's saying 3 decimal places. Okay, so we have to get the quadratic regression function. So we're going to go y1 tilde ax1 squared plus bx1 plus c. Just note as well, if you forget to type a 1, let's just say, it won't work. All right, again, when you do a regression analysis, you have to type in x1 and y1. I'll just change the color. There we go. Okay, so now we have our regression model. So that's good. And we want to snip this. Okay, so we're going to snip it. We want to capture everything here. So we'll snip it like that. Copy, and we'll paste that into Desmos. I mean, paste it into our Word doc and make that a little bit smaller. And we'll do what's next. Okay, so what we're going to do next now is type in the value for A, for B, and for C. So our A, and you can see these are all rounded. So we'll put the unrounded versions. So A is 0.0158834. So A is 0.0158834. The B value is negative 0.555155. And the C value is 15.5543. If you go back, we'll look at the R squared, it's 0.9997, so 99.97% accurate. All right, so pretty confident that this approximates a quadratic model. Okay, so our equation, again, I just tab over here. Okay, so our regression model was y1 tilde ax1 squared plus bx1 plus c. So then our equation, okay, instead of y and x, we have to use our contextual variables. So our y is the dependent variable, which is stopping distance d. So d would equal a. So we want 3 decimal places, 1, 2, 3. So the 5 is followed by an 8. So 0.016. Okay, that's our a value. Now for x, we write the variable s. So y equals 0.016 s squared minus, because that's a negative, the b 0.555, and that would be then s plus 15.554. That would be our regression model, and that would be our final answer. So again, what we did is that in places of A and B and C, we put the values that we got from Desmos. Why did we turn this plus into a negative? Because the B was negative. So that's why it's a minus. We replaced Y with D, X with S, because again, in this context, X is represented as speed S and Y is represented as stopping distance D. Okay, so we've got the model. Now we're going to use the model to solve problems. Okay, so we're going to compare the stopping distance at 25 kilometers per hour with the stopping distance at 50 kilometers per hour to the nearest tenth. So that means we're going to find the stopping distance at 50 kilometers per hour and the stopping distance at 25 kilometers per hour, and subtract the two values. Okay. So stopping distance is y. So we are solving for y. So we're going to plug in x equals 25, and we'll find y. Then we'll plug in x equals 50, and we'll solve for y. We'll do this on Desmos. So because we want the stopping distance, and we're given the speed is the x, so this is solving for y by plugging in x equals 25 and x equals 50. Okay, so we'll go to the third line. We'll go x equals 25. Okay, and that's that point. And then on the next line, we'll go x equals 50, and we'll click on those 2 points. So those are the 2 points that we want, and we're going to snip this graph so that way we show our work. Copy it and we'll paste. Okay, so we have the graph. So when, whoops, that's x equals 24, my bad. Oh, x equal, okay, so make sure we click on the right point. So 25, and then x equals 50. Okay, so we clicked on 25, clicked on 50, we're good. Now we'll re-snip the tool. So always got to be careful we click on the right points of intersection. And we'll copy that, and we'll paste that into our Word doc. Okay, so now, when x equals 25, y equals 11.603. And when x equals 50, y equals 27.505. So to compare the two, we're going to take 27.505 and we're going to subtract 11.603. Get that difference. Means that it takes longer for the car to stop when it's traveling at 50 versus 25, which is no surprise. So 27.505, and we'll subtract 11.603. We get 15.902. And it says to the nearest tenth of a meter. So final answer, the stopping distance at 50 kilometers per hour is 15.9 meters longer than the stopping distance at 25 kilometers per hour. We just solved a contextual problem, okay, finding out how much longer distance it takes the car to stop at 50 kilometers per hour versus 25. Okay. So the next question is asking, determine the maximum speed that the car should be traveling in order to stop within 7 meters. Just over the average length of a car. So we're given stopping distance of 7 meters and the speed, we don't know. We don't know the speed. So that means we know x and we are solving for y. So x, sorry, it's backwards. We know y and we are solving for x. So this is different, just opposite of what we did in the previous question. We are going to say that y equals 7 and we're going to find out the x value. So we'll go back to Desmos, we'll close those off, keep our graph, and now we are going to say y equals 7. And it doesn't touch. So I'm going to change this example to 17 meters. And I'll just delete that. So we'll say the stopping distance is 17. So y equals 17. Okay. So we have one on the left and one on the right. So obviously it can't be the negative speed. So it would be 37 kilometers per hour. So we will snip the graph with the intersection point. plug that in Desmos. And the speed, minimum speed, would be 37.39 kilometers per hour. Make sure that we round and make sure that we have units. That's how we would solve that. So x, so 17 was y, x was 37.386. Okay, so showing the work would be typing out what we're solving for, doing it in Desmos, clicking the intersection point, snipping the graph, copy pasting in, and then rounding our final answer. So what we've just done in examples to number 2 was used a quadratic model here to solve contextual problems. Okay, so moving on then to cubic regression. The process is no different, except we're just going to be using a different regression model. We will be using the cubic model instead. So we'll go to Desmos, we'll reset everything, and we will insert a table, and we'll look at the data. So we're going to determine the cubic regression model, and we will get this data in. So our x goes 0, 1, 2, 3, 4, 5, 6. So type that in, 0, 1, 2, 3, 4, 5, 6. And our y values, 0, 2, 5, 7, 8, 5, 0. 0, 2, 5, 7, 8, 5, 0. Sure I got that right. 0, 2, 5, 7, 8, 5, 0. 7, 8, 5, 0. Good. Okay. So if we look over here, this does not look like a parabola at all. Okay. So it goes up and down. So probably it's going to be cubic. It's not linear. It goes up and down, but it's not symmetrical. And so again, if we, let's just say we tried a quadratic, you didn't know. So we did y1 tilde ax1 squared plus bx1 plus c, you'd notice that we get an 89% r squared value. So it's trying to make the data fit. It is only about 80 to 90% accurate. So there must be a better model. So y1 tilde ax1 cubed, so a to the b3, so ax1 cubed plus bx1 squared plus cx1 plus d. And now we get a model that's 99% accurate. So we have a cubic model, okay, that matches this. And we have our a, our b, our c, and our d values. So we'll snip that. Copy and paste into our Word document. Okay. So what we can do now then is type our A, our B, C, and our D values. So we'll unround them. So A is negative 0.16667. The B value is 0.702381. The C value is 1.77381. And the D value is negative 0.095238. And so we want to get our cubic regression. So again, cubic was y1 tilde ax1 cubed plus bx1 squared plus cx1 plus d. So our equation then, y equals Okay, the two decimal places, A is negative 0.17, negative 0.17, B is 0.70, C is 1.77, and C is 0.095. Interesting. So now we have to round the 9 up, so it's negative 0.10. Okay, so we got our rounding, and now we plug it in. So y equals negative 0.17x cubed plus 0.70x squared plus 1.77x minus 0.10. And that would be our cubic regression model for that best approximates this data. So the only thing that's different is that we just used a different regression model. Okay, so that's how that works. All right, so we will look at our final example, which is solving a cubic regression equation problem in context. So the following data table shows the average retail price of gasoline, price P. So that will be our dependent variable, and the number of years N is our X, our independent variable. So the following data table shows the average retail price of gas per liter for a selection of years in a 30-year period beginning in 1979. So our N is the number of years after 1979. So obviously in 1979, N would be 0. This would be 1980, 81, 82, and so on. Okay, so our X, our Y. So we have some data points to plug in to Desmos. So we'll reset again. Okay, and we will begin. So our first 0, 1, 2, 8, 9, 12, 14. 0, 1, 2, 8, 9, 12, 14. 21.98. This data entry might be a bit long, but you can just copy paste the stuff over or just type it all out. Just have to go through the process of data entry. 47.53. 5705. 54.18. Okay, we'll do the next column. 17, 20, 22. 26, 27, 28, 29. Okay. 6, 27, 28, 29. Okay, so now price per liter 58.52. 59.43. 70.56. 92.82. 97.86. 102.27. And up 115.29. So we have all our data entered. It's a lot of data points. Make sure we have them. Okay. And now we want to see what we see. So we'll zoom out here, and you can see that we have something going on. It kind of doesn't really look like quadratic. So we are going to see what a cubic does. So we've got our scatter plot, and you're going to determine the regression equation to 3 decimal places. So we'll type y1 tilde a x1 cubed plus bx1 squared plus cx1 plus d. 99% accuracy, and we have our cubic regression. We will go to our data table. X is the number of years after 1979. And the y-axis is the price, the gasoline price. That's per liter. Dollars per liter. Okay. So we have our A, our B, our C, and our D values. So we'll snip that. Just do like that, move that over. Okay. So we'll snip that. Copy and paste. Okay. So our A, our B, our C, and our D. So our A is 0.0110729. Our B value is negative 0.417371. Our C value is 5.9717. And our D value is 22.2936. Okay, so our equation then from our regression. So y, instead of y equals x, we're going to say p, capital P, equals our a value. The 3 says 3 decimal places, 0.0111. Oops, 1, 2, 3. So 0.011. Our x is n. So p equals 0.011 n cubed minus 0.417 n squared plus 5.972, we round the 1 up to a 2, n plus 22.294. And that would be our cubic regression model that approximates the data for the price of gas in a 30-year period beginning in 1979 based on the data that we have. We used the cubic regression equation to estimate the price of gas in 2018. Is the estimate reasonable? Explain. Okay, so to get the gas price in 2018, actually let's change it to 2020. Okay, so gas price in 2020, that is our y value. So we need to know x, which is the number of years after 1979. So we can't say x equals 2020. Have to do, realize that x is going to equal 2020 minus 1979. So just to be on the down low here, 2020 minus 1979, we get 41 years. X equals 41, and we need to find what y is. So we'll go to our model. Oops, I'm going to change the color of that. Okay, and so x equals 41. And it's off our chart, so we'll zoom out. So we'll scale our graph. We'll say x goes from -1 to 50. makes it a bit better, and y-axis goes from -1 to 500. Okay, so just scaling it, we can actually see the cubic a bit better. And we can see our intersection point that we want. So that's the intersection point, so we can snip that. Copy paste into our Word document. And y equals 328.691. So therefore, in context, the price of gas equal dollars, right? We need units. That would be so this is cents, not dollars per liter. That would be, we have to divide that by 100, which is 3.28691. I think it was it dollars per liter or cents? Oh yeah, it was cents. So that's my mistake. That should be cents per liter. So I'm not going to change the graph, but that should be cents. So dollars then would be $3.29 per liter in 2020. And so that's what the model is telling us. This is not reasonable as current gas prices in real life, 66.9, I guess in dollars. Sorry, I'll put this underneath. Because gas is currently 0.67 per liter based on what I saw when I drove in today. So that's just an extension question, but the model is saying that it would be $3.29 per liter, okay? And it's not reasonable because it doesn't match what real life is. So these are just some examples of going through getting the regression equations and then using them to solve contextual problems. There are some text questions for homework that you can work on, and tomorrow there'll be a practice worksheet for this. And good luck working with polynomial regressions.